On a dark night, we often find ourselves gazing up at the stars, marveling at their shining beauty. Yet, have you ever pondered that stars are much more than mere twinkling lights in the vast expanse above? They're actually part of a much bigger picture, connecting us to the vastness of the universe. Think of stars as tiny pieces in a huge puzzle. They're not alone. They're linked to everything around them, including us. From the smallest particles to the biggest galaxies, stars are at the heart of it all. Stars have incredible lifespans, lasting for ages beyond our comprehension. Yet, they also go through changes that we can witness in our own lifetimes. Born from clouds of gas and dust, stars play a vital role in shaping the cosmos. They create the elements that make up everything around us, including life itself. We, too, are made of stardust. Our connection to the stars is ancient and profound, shaping who we are and where we come from. The video will delve into the exotica of this cosmic entity, along with the catastrophic deaths of these marvels. A star is like a big ball of hot gas that stays balanced. This balance happens because two forces, one pushing out and one pulling in, cancel each other out. The sun changes size because different forces push and pull on it all the time, but its structure adjusts to keep everything balanced. This balance keeps the star from collapsing or exploding. However, if this balance gets messed up, the star could collapse or explode. A star's size and mass decide how strong its gravity is, which affects the pressure and heat it needs to stay balanced. Stars, including the sun, use the pressure from their hot gas to push against gravity and stay stable. This pressure comes from the heat inside the star. At the same time, gravity holds the star together. As the star loses energy into space, its overall energy decreases. This causes changes in the star's temperature, following the rule that energy must be conserved. Stars, including the sun, rely on the pressure generated by their hot gas to maintain equilibrium, a pressure directly proportional to the star's thermal energy. Concurrently, gravity acts as the glue holding the star together. As a star emits energy into space, it undergoes a net loss of energy. However, a crucial question arises. What happens to its temperature amidst this energy exchange? Comparing a star to a brick can help us understand some interesting things. When a brick loses energy, it simply gets cooler. But a star acts differently because of gravity. As it loses energy, the star gets squeezed by gravity, which actually makes it hotter instead of cooler. This might seem strange, but it fits with the rule that energy is always conserved. On the other hand, if a star suddenly gets more energy, like from nuclear reactions, it works the opposite way. The increased temperature makes the star expand against gravity, which cools it down. This back and forth between heating up when losing energy and cooling down when gaining energy is important for understanding how stars change over time as they use up their nuclear fuel. At the heart of the weird happenings in stars are tiny particles called quantum particles. Things act differently in the world of atoms and tiny particles compared to what we see in our daily lives. This tiny world follows quantum theory, where changes don't happen smoothly but in sudden jumps. Even though these tiny particles are so small, their behavior affects big things like stars in significant ways. In the world we experience every day, objects like walls are solid and impenetrable. You can't simply pass your hand through a wall because it occupies space, and two objects cannot occupy the same space at the same time. This concept of impenetrability holds true in our macroscopic world. However, when we delve into the microscopic realm of quantum theory, things become much more nuanced. According to this theory, elementary particles, the building blocks of matter, exhibit behaviors that are vastly different from our everyday experiences. Rather than being solid, like little balls, particles also possess wave-like characteristics. In the quantum world, particles can exist in a state where their position is uncertain. This uncertainty is encapsulated by the famous Heisenberg uncertainty principle, which states that the more precisely you know the position of a particle, the less precisely you can know its momentum, and vice versa. This uncertainty extends to the energy of the particle as well. If the position of a particle is constrained in some manner, such as being confined within an atom, its momentum and energy become highly uncertain. Conversely, if you try to pin down the momentum of a particle, its position becomes less definite. Think of particles not as solid points, but rather as fuzzy entities, exhibiting a range of possible positions, momenta, and energies. This fuzziness allows for the possibility that more than one particle can occupy the same volume under certain circumstances. It's akin to the overlapping of waves on a pond, where multiple ripples can momentarily share the same space without cancelling each other out. Also, in the quantum world, certain particles, like electrons, protons, neutrons, and neutrinos, have a unique property called absolute impenetrability. This means they can't occupy the same space if they have the same momentum or energy, a rule known as the exclusion principle. However, they can share the same volume if they have different momentum or energy. For example, two electrons can't be in the same place if they have the same momentum, but they can if they have different momentum. Photons, on the other hand, don't follow this rule. Two photons with the same energy can occupy the same volume simultaneously. These rules, along with uncertainty, affect how atoms are built. Electrons move in a hazy cloud around the nucleus, and we can't pinpoint their exact spots because of their wave-like behavior and the uncertainty principle. They stay close to the nucleus because of its pull. Since some electrons have more energy, they can all fit in the same space while still following the exclusion rule. According to the exclusion principle, no two electrons can have the same set of quantum numbers, including energy level. However, within each energy level, there can be multiple electrons, as long as they have different quantum states, such as spin. So, even though electrons cannot occupy the same quantum state simultaneously, they can occupy the same space if they have different energies. This is why electrons with different energy levels can coexist in the same atom without violating the exclusion principle. As stars evolve, the unique characteristics of particles become crucial. Normally, particles within a star are scattered both in space and energy. This results in a thermal pressure that pushes outward, counteracting the star's gravity and maintaining its stability. However, as a star exhausts its nuclear fuel and contracts, it becomes denser. This compression forces electrons closer together. According to the exclusion principle, electrons with the same energy cannot occupy the same space. But if some electrons possess additional energy due to the compression caused by gravity and the uncertainty principle, they can share the same volume. As the available space for electrons decreases, their positions become more certain, but their energy becomes less predictable to satisfy the uncertainty principle. This leads to an increase in their average energy. Consequently, although the exclusion principle still prevents electrons with identical energy levels from occupying the same space, the restricted volume allows some electrons to gain extra energy. With this additional energy, they can coexist in the same volume, facilitating further compression of the star. When electrons within a star are compressed, they gain what's called quantum energy solely due to quantum effects. This energy depends only on the star's density and isn't affected by temperature. This quantum energy can exceed the normal thermal energy by significant margins. These energized electrons can also generate what's known as quantum pressure. This pressure can uphold the star even if the thermal pressure isn't sufficient. Because quantum pressure remains constant regardless of temperature changes, stars supported by it don't contract when they lose energy by radiating heat into space. Instead, they cool down like regular matter. Stars upheld by the quantum pressure of electrons are termed white dwarfs. However, there's a limit to the mass they can support, known as the Chandrasekhar mass, after the physicist who first calculated it. If a white dwarf accumulates too much mass, it can collapse or potentially explode, thus giving one of the biggest catastrophes of the universe. Now that we've gained a basic understanding of the quantum behavior of particles, let's progress and explore the process through which stars come into existence. Stars come to life as protostars, emerging from the chilly clouds of gas floating in space. These protostars form when big clumps of gas collapse under gravity's pull, becoming denser and hotter with time. Eventually, when the pressure and temperature inside reach extreme levels, nuclear fusion sparks, marking the birth of a star. Sometimes, shock waves from cosmic events like supernovas can also kickstart the formation of protostars. In their early stages, protostars aren't hot enough to sustain nuclear fusion. However, they emit energy into space, gradually warming up over time. This warming process is driven by the interplay of gravity and energy conservation laws. As they continue to radiate energy and heat up, protostars inch closer to the critical temperature needed for fusion to ignite. Once this threshold is reached, they transition into fully fledged stars, illuminating the cosmos with their radiant brilliance, each a mesmerizing beacon in the vast expanse of space. When you randomly pick someone, they're often middle-aged, not too young or too old. Similarly, if you pick a star from the night sky randomly, it's probably in its main phase, called the main sequence. This is where stars spend most of their lives, mainly burning hydrogen. Stars, mostly made of hydrogen, spend the majority of their active years in this main sequence phase, where hydrogen undergoes burning. It's like how humans spend most of their lives as adults. For example, our Sun is in the main sequence phase now, about halfway through its 10 billion year lifespan. Bigger stars burn hydrogen faster because of higher pressure and temperature, leading to shorter lifespans. Smaller stars burn it slower and live longer. Stars with less than about 80% of the Sun's mass have barely started evolving. As the universe is still young, a star burns its hydrogen at a consistent rate because it regulates its burning precisely, using the principle of energy conservation that ignited the fuel in the first place. If the nuclear furnace produces slightly more heat than the star can radiate away, the excess heat increases pressure and causes the star to expand. This expansion consumes more energy than the nuclear belch produced, cooling the star slightly. As the star expands and cools, nuclear burning slows down because reaction rates depend on temperature. This creates an efficient negative feedback loop. If the star produces too much heat, expansion reduces nuclear fires to restore balance, and vice versa. It's similar to how a thermostat and furnace work in a house. If it gets too cold, the furnace kicks in to restore warmth. If it gets too hot, the furnace turns off until the temperature returns to normal. The process of hydrogen burning on the main sequence is called thermonuclear fusion. It involves combining hydrogen nuclei to form helium nuclei, which consist of 2 protons and 2 neutrons. This fusion relies mainly on the nuclear force, which binds the particles in the helium nucleus together. The extra energy released during this process becomes heat. While similar to ordinary burning, where chemical forces bind molecules and release energy as heat, nuclear burning is much more powerful because the nuclear force is stronger than the electrical force. The energy released from hydrogen fusion into helium is significant, about 1% of the maximum energy that could be released if all the hydrogen's mass were converted into pure energy according to E=mc². This high energy release efficiency makes thermonuclear bombs potent weapons and raises hopes for controlled thermonuclear fusion as a promising future energy source. Let's take a closer look at how hydrogen turns into helium. There are various methods for this, but they all share a common feature. In thermonuclear fusion, 4 protons combine to form helium. During this process, 2 protons need to change into 2 neutrons. This transformation happens because of the weak force, which can convert protons into neutrons and vice versa. To understand this fully and its practical implications, we also need to consider the laws of conservation of charge and baryons and leptons. Baryons and leptons are 2 groups of particles. In the mid-20th century, as particle physics was developing rapidly, physicists were discovering an increasing number of particles in experiments. To make sense of this complexity, they sought to classify particles into groups based on shared characteristics. Baryons and leptons emerged as 2 such groups. Baryons are a class of particles that include protons and neutrons, the building blocks of atomic nuclei. They are characterized by being composed of 3 quarks, held together by the strong nuclear force mediated by gluons. Introducing the concept of baryons helped physicists understand the structure of atomic nuclei and the strong force interactions within them. Leptons are another class of elementary particles that include electrons, muons, tau particles, and their corresponding neutrinos. Unlike baryons, leptons do not participate in a strong nuclear force. Instead, they interact via the weak nuclear force and electromagnetism. Introducing leptons provided a framework for understanding phenomena such as beta decay and neutrino interactions. The introduction of baryons and leptons was also motivated by the need to formulate and understand conservation laws in particle interactions. For example, in many particle interactions, quantities such as baryon number and lepton number are conserved. These conservation laws are fundamental principles in particle physics and help to predict and interpret the outcomes of particle interactions. Now, in the core of a star, during hydrogen fusion, when 2 protons convert into 2 neutrons, the total number of heavy particle baryons remains unchanged, starting with 2 and ending with 2. Both neutrons and protons are baryons. However, this change can't occur on its own because it doesn't conserve charge. The positive charge on the protons can't just vanish. To keep the charge balanced and maintain no overall change in charge, 2 positively charged particles need to be generated. These particles can't be any type of baryons, since the reaction already balances the number of baryons. Nature addresses this by offering positrons, a type of lepton. When 2 protons become 2 neutrons and 2 positrons, there's no net charge. Nevertheless, since we're introducing 2 new leptons, the reaction must also produce 2 other leptons alongside the neutrons to keep the lepton number balanced. Positrons have the opposite charge and lepton property from electrons and count as -1 lepton each. The other leptons emerging from the reaction must carry no charge but count as +1 in terms of leptons to counterbalance the positrons. To simultaneously balance charge, baryons, and leptons in this reaction, nature supplies the neutrinos. And with this at the end of the reaction releases a huge amount of energy which powers stars. Now, we've discussed the formation of stars and their energy sources. However, a new concept introduced in this process is neutrinos. Let's explore this term further and unravel its significance. Hydrogen undergoes fusion, generating neutrinos at the cores of stars where temperatures are at their highest. Because neutrinos interact solely through the weak force, conventional stellar matter is essentially transparent to them. Consequently, neutrinos produced in the core hydrogen fusion reactions swiftly exit the star at nearly the speed of light, carrying away a small amount of energy that would otherwise contribute to heating the star, though this loss of energy is relatively insignificant. However, what makes neutrinos significant to astronomers is that they originate directly from the star's core, conveying valuable information about its conditions. In contrast, astronomers typically rely on studying photons emitted from the outer surface of stars to infer their inner structure. While analyzing these photons is a potent method for deducing the nature of a star's inner regions, it cannot fully replace the direct observation provided by neutrinos originating from the Sun. Observing the Sun's core using neutrinos poses a challenge because neutrinos pass through any detector without obstruction, similar to how they freely exit the star. Detecting neutrinos requires deploying an extensive detector and patiently awaiting the rare occurrence of a reaction within it due to the weak force. However, this approach is entirely infeasible for stars other than the Sun, because the significant distance diminishes the brightness of neutrinos from a distant star as rapidly as it affects visible photons. Ray Davis and his collaborators achieved the first successful detection of neutrinos from the Sun after a multi-decade endeavor. The detector was made up of a large amount of chlorine-rich cleaning fluid, approximately 100,000 gallons. Neutrinos interacted with chlorine through the weak force, causing a neutron in a chlorine nucleus to transform into a proton, leading to the creation of radioactive argon. The argon could be efficiently collected as it is a noble gas and doesn't chemically combine. The detector tank was placed at the bottom of the Homestake gold mine in Lead, South Dakota, to shield it from cosmic ray particles that might trigger false reactions. The mine, previously inactive, was reopened when the price of gold surged, but later ceased operations and flooded. Efforts are being made to repurpose the mine for underground physics research, though success is uncertain. Initially, the solar neutrino experiment yielded no signal above the background noise of unrelated reactions, causing concern in the astronomical community. However, with patience, a positive signal was eventually detected, despite only a few hundred argon atoms being collected monthly from the vast fluid volume. The detection of some neutrinos provided some reassurance. Nonetheless, a significant issue arose as the observed number of neutrinos was considerably lower than what was predicted by the standard computer model of the Sun. The difference could originate from various factors. Nuclear reactions might occur differently from our expectations. The Sun's structure might be altered in some way. It's possible that the composition, especially of heavy elements, isn't evenly spread throughout, as assumed. The properties of neutrinos themselves could also vary. The gold mine experiment focuses on one type of neutrino produced when protons convert to neutrons, but there are other types. If neutrinos change into one of these other types during their journey and don't induce the expected reaction, they won't be detected. Recent progress may provide a solution to this puzzle. One encouraging finding came from a neutrino detector called Kamiokande in Japan. Unlike the chlorine experiment, Kamiokande uses water and can observe neutrinos in real time, determining their direction of travel. Neutrinos interacting with the water can cause reactions, producing particles that emit a blue light called Cherenkov radiation, allowing the tracking of neutrino direction. Kamiokande detected the same type of neutrinos as the chlorine experiment, confirming they originated from the Sun. Without this confirmation, there was a chance the home state detection was due to local contamination, which would have complicated the problem further. A recent breakthrough could hold the key to understanding. The home state and Kamiokande experiments focus on detecting a small number of high-energy neutrinos produced by a rare type of hydrogen burning process. Changes in the Sun's interior might affect this process without altering its overall energy output. However, these experiments cannot detect the much larger number of low-energy neutrinos produced by the basic reaction responsible for the Sun's radiation output. Another experiment, involving gallium as a detector and planned in collaboration with Russian physicists, also failed to observe the expected rate of neutrinos. This suggests that our understanding of neutrinos is incomplete. As mentioned earlier, there are 3 types of neutrinos, each with their antineutrinos, corresponding to the 3 types of quarks that make up particles like protons and neutrons. Initially, neutrinos were thought to be massless, but theories combining strong and electroweak forces propose they have a small mass. According to these theories, neutrinos can convert from one type to another as they travel. If this conversion occurs repeatedly, by the time neutrinos reach Earth, there could be roughly equal amounts of all 3 types. This would explain why only about 1/3 of the expected neutrinos from the Sun are observed by experiments designed to detect a specific type. This understanding of the solar neutrino experiments strongly implies that we may have finally resolved the solar neutrino issue and obtained compelling evidence for the grand unified theory of elementary particles. While this seems to be the answer, it also poses the challenge of conducting more experiments to validate this hypothesis. A significant advancement occurred in the summer of 1998, when scientists working on the Super Kamiokande experiment in Japan announced a breakthrough. This experiment provided evidence that neutrinos change from one type to another as they interact with the Earth's atmosphere, indicating they must possess mass, as predicted by theory. While the mass itself is not directly measured, detecting differences in masses represents a significant step forward. However, to fully explain all the data from various experiments, there is some discussion regarding the necessity of introducing another type of neutrino known as a sterile neutrino, which interacts solely with neutrinos and no other particles. Now that we've delved into the fundamental nature and evolution of stars, let's embark on an exhilarating journey into their demise. The spectacular ends of stars on cosmic scales are among the most monumental events in the universe. The Sun may seem unchanging to us, but it's actually evolving over time. We can notice this change just by feeling the warmth on our faces when it's sunny outside. This warmth comes from the Sun's energy, which it sends out into space. Since nothing from space replaces this energy, the Sun is gradually losing energy overall. This means something must be happening inside the Sun to change it slowly but surely. One big change happening inside the Sun is its composition. It's turning some of its hydrogen into helium, and this change can't be reversed. This transformation is happening gradually but steadily. Eventually, these changes will have a big impact. In the center of the Sun, where it's hottest, hydrogen is being used up and helium is building up. but the cooler outer parts of the Sun still have their original composition. This causes the Sun to act in two ways at once. It shrinks and swells. This follows the rule of conserving energy, but it's more complicated than for stars with the same composition throughout. When the center of a star runs out of hydrogen, it becomes mostly helium, with a few other heavy elements scattered in. The rest of the star still has mostly hydrogen. As the star changes over time, the difference between the changed inner part and the unchanged outer part becomes clearer. We call the inner part the core and the outer part the envelope. The helium in the core can be used as fuel for nuclear reactions, but it doesn't happen by itself. The nuclear force, which makes these reactions possible, only works when particles are very close together. However, there's another force, the electrical force, that pushes particles apart because they have the same charge. Without other forces like gravity, this electrical repulsion would stop nuclear reactions from happening. To start nuclear burning, the repulsion between protons' charges needs to be overcome. Although the electrical repulsion is weaker than the nuclear force, it has more influence over longer distances, especially when particles are far apart. However, when particles get closer, the nuclear force takes over and binds them tightly. But to bring these charged particles close enough for the nuclear force to act, some energy must be spent to push them together despite the resistance from electrical repulsion. Essentially, you have to invest energy to overcome the charge repulsion, but the energy released by nuclear reactions makes this investment worthwhile. In practice, we overcome charge repulsion by giving the particles heat energy. This makes them move more energetically, increasing the likelihood of collisions and bringing them closer together for nuclear reactions to occur. Just like you need to heat wood with a match and kindling to start a fire in a fireplace, a protostar needs to contract enough to heat its hydrogen sufficiently to begin burning. Since helium nuclei have 2 protons compared to hydrogen's 1, the repulsion is stronger, requiring even higher temperatures to initiate thermonuclear reactions. When a star runs out of hydrogen in its center, it needs to become even hotter to start burning helium. It handles this naturally by conserving energy. Once the hydrogen is used up, no more energy is produced. Without heat input, the pressure inside the star decreases, causing it to contract. This contraction generates heat until the helium becomes hot enough to burn. The same process that triggered and regulated hydrogen burning now sparks helium burning once the hydrogen is depleted. Here's where things get interesting. The helium core contracts and heats up until helium starts burning. Interestingly, this contraction releases more heat energy than the core requires. The excess heat flows into the outer layer of the star, made of original material. The outer layer reacts oppositely to the core. Feeling the excess heat, it expands against gravity and cools down. So, the star simultaneously contracts, heats up at the core, and expands and cools down at the outer layer. The contracting core plays a crucial role in the star's long-term evolution. But what astronomers observe through their telescopes is the outer layer of the envelope. As the outer layer, along with the entire envelope, cools down, it appears redder in color. Meanwhile, inside the star, helium burns rapidly, making the star shine brightly. Astronomers classify the brightest stars as giants and the dimmer ones as dwarfs, based on their surface temperature. The stars we're discussing have become what astronomers call red giants. As the envelope expands, the size of these stars grows significantly, making them giants not only in brightness but also in size. However, it's important to note that when astronomers refer to a star as a giant, they're not strictly referring to its size. For example, a blue supergiant can be much brighter than a red giant despite being smaller. Nonetheless, red giant stars swell from the size of the Sun to extend well beyond the orbits of the inner planets of the solar system. We anticipate the Sun to undergo this transformation in about another 5 billion years, during which time it will spend roughly 1 billion years, or about 10% of its total lifetime, as a red giant before reaching the end of its life. To be honest, this explanation for how a red giant forms, through the exchange of energy from the core to the envelope, is somewhat oversimplified. While energy exchange does play a role, experts still debate the best way to understand the formation of red giants. Computer models of stellar death illustrate that it does occur, but it's a complex process involving nonlinear interactions between the star and gravity. It's not easily explained by pinpointing a single key factor. In a way, the formation of a red giant involves instability. It's comparable to pushing a book toward the edge of a table. Initially, not much happens, but if you push too far, the book falls to the floor. Similarly, as the core of a star contracts after consuming its central hydrogen, there's a point where the outer envelope falls outward, reaching a lower energy state that balances the pressure in the core and envelope with gravity. Stars of significant mass go through multiple burning stages after they evolve into red giants. They spend roughly 10% of their total lifespan in this phase, with each stage progressing faster than the previous one. When each successive fuel source is depleted in the core, the star loses its heat source, causing the core to contract until the material formed in the previous burning phase becomes hot enough to ignite. The core needs to reach a high enough temperature to overcome the charge repulsion among an increasing number of protons in increasingly complex nuclei. In massive stars, hydrogen burns to form helium. While the specifics differ from those of the Sun, the overall outcome remains the same. 4 protons combine to form a helium nucleus, accompanied by the creation of 2 neutrinos. For stars like the Sun and those more massive, helium burning transforms helium into carbon and then oxygen. This occurs because the simplest interaction, combining 2 helium nuclei, produces a nucleus with 4 protons and 4 neutrons. However, due to the details of how the nuclear force operates, the nuclear attraction of this combination isn't strong enough to overcome the charge repulsion of the 4 protons. This combination is unstable and breaks apart, preventing it from being a step in the nuclear burning process to produce heavier elements from a given fuel source. Nature overcomes this bottleneck by occasionally allowing 3 helium nuclei to come close enough to combine under the influence of the nuclear force. The outcome is a nucleus containing 6 protons and 6 neutrons, which forms the element carbon, the very element essential for life as we know it. As helium continues to burn in this manner, some of the remaining helium can combine with the newly formed carbon to produce oxygen, another crucial element for life. In the case of the Sun, thermonuclear burning is expected to cease once carbon and oxygen are produced. However, in stars with sufficient mass, this process persists, leading to the formation of a variety of heavier elements. Among these are neon, magnesium, silicon, sulfur, argon, calcium, and titanium. Although this assortment may seem diverse, ranging from noble gases to elements found in bones to metals used in submarine hulls, they all share a common characteristic. Each subsequent element contains 2 more protons and 2 more neutrons than the one before it. Stars produce this succession of elements abundantly because each is essentially built from the basic components of helium nuclei. 3 for carbon, 5 for neon, and 10 for calcium. As each phase of burning fuses lighter nuclei into heavier ones, the number of protons increases, requiring higher temperatures to overcome the increased charge repulsion. Consequently, the star responds by contracting, raising the temperature in the core whenever it lacks nuclear energy input to offset the radiation lost to space. This fascinating phenomenon, which extends the lifespan of a star, ironically tightens its grip under the force of gravity. Eventually, gravity will emerge victorious in this celestial conflict, leading to the inevitable collapse of the star's core. Now, let's explore the process of core collapse in stars. Massive stars evolve through a series of changes, gradually building up heavier elements within their cores until they reach the formation of iron. Iron is particularly significant due to its tightly bound nucleus, which attracts other elements towards it. It acts as a gravitational low point in the nuclear landscape, analogous to the bottom of a valley, where elements naturally converge under the influence of the nuclear force. Elements lighter than iron exhibit a strong inclination to combine and transform into iron, yet they are hindered by the repulsion between their protons. However, stars act as agents of fusion, overcoming this repulsion and facilitating the process of elements merging toward the iron core. This mechanism is essential for maintaining the stability and energy balance within stars. Energy cannot be extracted from a rock at the valley's bottom. Instead, energy is needed to move it back up the hill. Similarly, a stellar core composed of iron cannot produce nuclear energy. As the star loses energy, gravity compresses the iron core, causing it to break apart and absorb heat energy. This process prevents the core from generating pressure to counteract gravity, leading to the star's collapse. The formation of an iron core in a massive star marks the end of its nuclear life, ultimately resulting in a catastrophic collapse. During the collapse, as iron breaks down into lighter elements, the core contracts, leading to a significant increase in density. Despite the growing quantum pressure exerted by electrons, it becomes insufficient to counteract gravity. Eventually, the electrons yield to gravity and undergo a process where they combine with protons, resulting in their mutual transformation into neutrons, driven by the principle of charge conservation. To maintain lepton number conservation, the disappearance of each electron necessitates the production of a neutrino. Consequently, in the collapse of the iron core, electrons and protons vanish, replaced by neutrons and a flurry of neutrinos. This process gives rise to the birth of a completely new astronomical entity known as a neutron star. A neutron star consists predominantly of neutrons and typically possesses a mass slightly greater than that of the Sun. Yet it maintains an incredibly compact size, with a radius of around 10 kilometers, roughly comparable to that of a small city such as Austin. The density at the core of a neutron star surpasses even that found within atomic nuclei, highlighting its extraordinary nature as a massive atomic nucleus bound together solely by the force of gravity. Achieving densities of approximately 10 to the power of 15 grams per cubic centimeter. A neutron star represents an astonishing compression where the equivalent of an entire city like Austin would need to be condensed into the size of a sugar cube. The gravitational pull exerted by a neutron star is immensely powerful, necessitating a counterbalancing pressure of equal magnitude. At sufficiently high densities, the quantum pressure exerted by neutrons, augmented by the nuclear force, becomes capable of overcoming gravity and maintaining dynamic equilibrium within the star. This nuclear force, akin to gravity or charges of opposite polarity, is attractive over large distances but becomes repulsive at close proximity, aiding in the dispersion of densely packed neutrons and contributing to the internal pressure that upholds the neutron star structure. Similar to white dwarfs, Neutron stars also have a maximum mass beyond which their internal pressures cannot sustain further gravitational collapse. While the quantum effects are well understood, the precise nature of the nuclear force introduces some uncertainty into this maximum mass, with estimates suggesting it lies in the range of 1.5 to 2 times the mass of the Sun based on sophisticated calculations of nuclear interactions. The collapse and subsequent restoration of support by the quantum pressure of neutrons and the repulsive nuclear force among densely packed neutrons occur swiftly. This process unfolds within a mere second in a star that has experienced millions of years of tranquil existence. The formation of a neutron star following core collapse is not guaranteed. The collapse releases an immense amount of gravitational energy, far exceeding what's needed to expel the outer layers of the star. Neutrinos carry away the majority, over 99% of this energy. They escape from both the collapsing iron core and the newly formed neutron star, dissipating most of the energy into space. It remains unclear how much of the remaining energy from the collapse can be directed outward. If enough energy expels the surrounding layers of the star, a neutron star can remain. However, if insufficient energy is directed outward, the outer layers collapse inward. Although a neutron star may briefly form from the collapsed core, the remaining mass of the star exceeds what a neutron star can support. Consequently, the neutron star is swiftly crushed out of existence in a process of total collapse, resulting in the formation of a black hole. A black hole represents an entity where all mass has been compressed to effectively zero volume, leaving only an overpowering gravitational field near the center of the collapse. Neutron stars are enigmatic entities, but there are systems in which two or more stars orbit each other due to gravitational force. Let us delve into the enigmatic journey of the evolution of those binary star systems. Stars can be found in various arrangements. While single stars and pairs are the most common, some systems contain 4 or even 5 stars orbiting each other. In this part of the video, our focus will be on systems with a pair of stars, also known as double stars or binary stars. Binary stars can be categorized into 2 main types: wide and close binaries. Wide binaries consist of stars in large, long-period orbits, likely formed by the chance gravitational capture of 2 stars born separately. These stars evolve independently, much like single stars, and their gravitational pairing is of lesser concern in this discussion. More intriguing are the close binaries, likely formed from the fragmentation of a single protostellar clump. Similar to the formation of triple and quadruple systems, these close pairs are significant because the presence of a nearby companion significantly influences the evolution of the stars involved. The orbits of a pair of stars are governed by the force of gravity and the principles of conservation of linear and angular momentum. Linear momentum is determined by multiplying the mass by velocity, while angular momentum, or spin, is calculated by multiplying mass, velocity, and the size of the object. Stars often move around each other in curved paths called orbits. While we often think of these paths as circles, they can be more stretched out, like ovals. In reality, even though they're not perfect circles, it's still okay to imagine them that way for most of what we're doing. When stars orbit each other, they move in opposite directions. This might seem a bit odd, but it's important for keeping things balanced. If they both moved in the same direction, it would break a rule of nature called the conservation of momentum. If the stars are different sizes, their paths will also be different. The smaller star has to zip around faster to make sure everything stays in harmony. Even though it's moving faster, both stars take the same amount of time to complete one orbit around each other. So, the smaller star has to travel a longer distance to catch up. The way planets move around the Sun follows similar rules. They travel in big loops around a point called the center of mass, which sits somewhere between them and the Sun. Meanwhile, the Sun isn't completely still either. It also moves in a small loop around this center of mass. This loop is about the same size as the Sun itself, and the Sun moves at a speed of roughly 30 miles per hour, which might seem slow, but it's enough to be measured. Scientists have recently found other stars with big planets nearby by measuring similar movements. The Sun's loop is quite complex. Even though it's mainly influenced by Jupiter, it's actually trying to loop around the combined center of mass of all 9 planets at once. Using carefully collected data on planetary motion, Johannes Kepler, inspired by his mentor, a Danish astronomer, inferred empirically that planets move in elliptical orbits and that the time it takes for a planet to complete its orbit is directly related to the size of its orbit. The angular momentum of 2 stars orbiting each other is influenced by their mass and speed, similar to linear momentum. Additionally, the size of their orbits affects their angular momentum. As a result, angular momentum plays a crucial role in determining the size of orbits for stars with specific masses and velocities. Kepler's second law of orbital motion arises from the constancy of each star's angular momentum around the center of mass. Thanks to Newton's law of gravity, we now understand Kepler's third law to mean that the square of an orbit's period is directly related to the cube of the orbit's size, divided by the combined mass of the 2 stars in orbit. This law is immensely significant in astronomy. The connection between period, orbit size, and mass offers a relatively straightforward method for measuring the masses of stars. When studying a binary star system, astronomers can measure the period quite easily and the separation between the stars, although with some difficulty. Using these 2 pieces of information and Kepler's third law as explained by Newton, astronomers can calculate the total mass of the system. However, to determine how much mass each star possesses, astronomers need additional data. One key reason why the investigation of double star systems holds such importance is that they offer direct insights into the masses of stars. Each star in a binary system exerts gravitational influence that extends beyond its own surface. The more massive star, larger the sphere of influence. By carefully mapping out these regions of influence for each star, considering the complexities of their orbital movements, we observe that the boundary where these regions meet resembles a figure-8 shape when viewed in cross-section. These 2 halves of the figure are termed Roche lobes, named after the German scientist who first mathematically described their form. The significance of these gravitational lobes is so profound that discussions on binary stars often include a depiction of this famous figure. The connection point between the 2 lobes of the figure is referred to as the first or inner Lagrangian point, named in honor of the French mathematician Lagrange, who extensively studied these systems. This point marks the spot in space where the gravitational pull from the 2 stars is perfectly balanced. Any slight shift in either direction would cause matter to drift towards one of the stars. Beyond the boundaries of the Roche lobes, matter doesn't belong to either star but rather comfortably orbits around both of them. Moving outward from the stars along a line, we encounter the second and third Lagrangian points. Beyond these points, the centrifugal forces surpass the gravitational pull of the stars, potentially causing matter to escape the system entirely. At right angles to the line between the stars lie the 4th and 5th Lagrangian points. While not particularly relevant in our current discussion, These points hold significance in the realm of space colonization. The L5 Society, whose emblem was the fifth Lagrangian point, recognized the potential of these points for space colonization. The fourth and fifth Lagrangian points are positions where a third body can remain stably locked within the gravitational field of the two primary objects. This concept suggests that these points could be ideal locations for establishing artificial space colonies, perhaps between Earth and the Moon. Stars of greater mass have more fuel at their disposal, yet they use it up quickly. This means that massive stars have much shorter lifespans than smaller ones, which conserve their limited hydrogen fuel. For instance, consider Algol, a prominent multiple star in the Perseus constellation and one of the earliest non-nova variable stars to be identified. Algol appears blue-white to the naked eye and exhibits periodic fluctuations in brightness, alternating between brighter and dimmer phases every few days. During its dimmer phases, Algol takes on a slightly redder hue. In some ancient cultures, a red, flickering light in the sky was considered ominous, leading to Algol being dubbed the demon star, with Algol deriving from the Arabic word for demon. We now understand that Algol is a binary system, with one of the stars being an evolved red giant, which contributes to its red appearance. The fluctuating brightness is due to our vantage point almost aligning with the orbital plane of the stars, allowing us to observe eclipses as each star passes in front of the other. The reddening effect occurs because more light from the red giant is visible during its eclipse of the blue-white companion. Additionally, because one star has evolved into a red giant while the other remains on the main sequence, we can infer which star is more massive, since the red giant has already undergone significant evolution. It must be the more massive of the two stars. This is wrong. By utilizing the measured period, employing certain astronomical techniques, and leveraging Kepler's reliable third law, we can determine the masses and ascertain that the red giant possesses approximately 0.5 solar masses, while the main sequence star boasts 2 to 3 solar masses. This scenario presents the Algol paradox. How can the evolved star be less massive? To reconcile this paradox, we adhere to the notion that the red giant must have originally been the more massive star to undergo evolution first, which aligns with our fundamental principles. The key to resolving this paradox lies in recognizing that, unlike most solitary stars, close binary systems like Algol do not maintain their original masses. In such systems, one star can transfer mass to the other. Initially, the more massive star becomes a red giant and then transfers mass to its companion until the mass ratio completely reverses. The formerly more massive star becomes the less massive, while the initially less massive star becomes the more massive. To understand the process of mass transfer in binary systems, we need to revisit the concept of Roche lobes, symbolized as the cult symbol. Even in a binary setup, the evolutionary journey follows its usual path. Two stars forming a close binary system likely originate from the same interstellar gas fragment, suggesting they're fraternal, not identical twins. It's highly improbable for them to have identical masses. Typically, one star will be notably more massive than the other. The more massive star depletes its hydrogen supply at its core first, initiating its evolution. As the core contracts and the envelope expands, the star transitions into a red giant. Due to its greater gravitational influence, the more massive star possesses a larger Roche lobe. However, this lobe's size is finite, approximately equal to the distance between the stars. As long as the stars remain closer than the eventual size the red giant would typically achieve, the presence of the companion star disrupts the standard evolutionary process. This disruption serves as the fundamental criterion for classifying a binary system as a close binary system. The narrative shifts when the more massive star expands to the extent that it fills its Roche lobe. Despite the ongoing internal forces causing core contraction and envelope expansion, once the outer regions of the star surpass the Roche lobe, they escape the gravitational pull of their originating star. Consequently, the matter that extends beyond the star's Roche lobe no longer pertains to that star alone. While some of the mass orbits both stars, a significant portion is funneled through the neck at the inner Lagrangian point to rapid alterations in the stars. To understand this, let's revisit the characteristics of Roche lobes. The larger lobe belongs to the more massive star. As this star evolves and fills its lobe, it begins shedding mass. Consequently, with the star losing mass, its gravitational influence diminishes, causing its Roche lobe to contract. Matter previously bound to the star now becomes detached due to the reduced size of the Roche lobe, resulting in further mass loss and a consequent reduction in the size of the Roche lobe. This process creates a positive feedback loop. The more mass the star loses, the more it's compelled to lose. Initially, the more massive star only experiences mass loss at a relatively slow pace dictated by core contraction. However, once mass loss initiates, it accelerates rapidly, irrespective of internal structural changes within the star. This accelerated phase persists until both stars achieve equal mass. The process unfolds. The stars progressively approach each other while mass is exchanged. This mechanism is predominantly governed by the principle of conserving angular momentum. When mass is transferred to the less massive star, which moves at a higher velocity, an excess of angular momentum arises. In response to this imbalance, the stars draw closer together, as a smaller orbit implies reduced angular momentum. Although the pace slackens, the transfer of mass persists even after the stars achieve mass parity. At this stage, the conservation of angular momentum drives the stars to spiral apart. As the star continues losing mass, it transforms into the smaller, higher velocity star. Without an adjustment, angular momentum would decline, necessitating the movement to a larger orbit as mass shifts from the faster-moving star to the slower one. The inclination for the stars to move apart once the mass-shedding star becomes less massive implies that its Roche lobe expands rather than contracts as mass diminishes. To sustain mass transfer, the star must expand to occupy its newly enlarged Roche lobe. Although this expansion occurs, it unfolds over a longer time scale dictated by internal structural changes as the core contracts. With the absence of a positive feedback loop, the pace of mass transfer slows. Nonetheless, it persists until the star ceases its progression toward becoming a red giant. Presumably, the Algol system is currently in this phase of gradual mass transfer. When two stars are relatively far apart, but still close enough to be considered a close binary, mass transfer typically begins once the more massive star evolves into a nearly fully developed red giant. During this process, the star losing mass will have a large surrounding envelope and a small core. Mass transfer continues until almost all of the envelope disappears, leaving only the core behind. If the original star was not overly massive, less than about 8 times the mass of the Sun, the remaining core will be dense and supported by quantum pressure. Eventually, it will cool down to become a white dwarf. As a result, there will be a small white dwarf orbiting around a larger main sequence star. The main sequence star gains mass because it absorbs much of the envelope matter that once surrounded the white dwarf. A more massive star, originally more than about 8 times the mass of the Sun, can leave behind a larger core, supported by thermal pressure. This core can continue to evolve by contracting and heating until new nuclear fuels ignite in its center. In this scenario, the core may develop an inner iron core that could undergo collapse, leading to either the formation of a neutron star or a black hole. Consequently, various types of compact stellar remnants, white dwarfs, neutron stars, or black holes could orbit a normal star in a binary system. If the two stars are very close together, their evolution takes a different path. During their time on the main sequence, stars slightly increase in size as they use up their hydrogen. This happens because the helium produced in their cores takes up less space than the hydrogen did. As the helium contracts, the outer parts of the star gain energy from the gravitational energy released, causing them to expand and cool slightly. This process resembles the expansion that occurs when a star becomes a red giant, but on a smaller scale, if the stars are extremely close. Normally, the star losing mass is a red giant evolving rapidly, while the mass-receiving star, still on the main sequence, remains passive. However, in this scenario, both stars are still on the main sequence. The mass-losing star evolves slowly, continuing to transfer mass to its companion, which accelerates its evolution as it gains mass. For close stars, the second star also swells to fill its Roche lobe. Both stars then attempt to transfer mass to each other simultaneously, leading to a messy situation. One consequence of both stars pushing mass beyond their Roche lobes is the formation of a disk surrounding both stars, orbiting in the same plane as their orbit. This matter flows outward into the disk, giving rise to what is called an excretion disk. Some material from the system may be ejected entirely into surrounding space. Computer simulations suggest another intriguing possibility. When both stars try to transfer mass to each other, only one can succeed. Depending on the perspective, either the smaller star loses all its mass to the larger one or the larger one consumes the smaller one. The result is not an exotic binary system, but a single star, possibly surrounded by an excretion disk, serving as the sole evidence of the cannibalistic event. In the conventional scenario, where the initially less massive star stays on the main sequence while the other star completes its evolution, the second star eventually undergoes its own transformation. The second star will deplete the hydrogen in its core, possibly including some contributed by the other star. Subsequently, the second star will begin to expand as its core contracts, eventually filling its Roche lobe as well. At this juncture, the second star initiates the transfer of mass to the first star. The second star is indifferent to the form of its companion. Its primary objective is to transfer mass to it. From an astronomer's perspective, this situation can be quite intriguing because the recipient star could be a white dwarf, a neutron star, or a black hole. All of these stars' remnant exists with substantial gravitational fields. The outcome can be quite remarkable. Astronomers have observed numerous systems where a star transfers mass to a compact star. While some of these binary systems with compact stars may have evolved as described earlier, with the second star simply expanding to fill its Roche lobe, in other cases, the actual evolution is likely to be more intricate. The main element that can disrupt the straightforward scenario of one star filling its Roche lobe and transferring material to the other star, which passively receives the mass, is that the second star is unlikely to be entirely passive. The star gaining mass can oppose the process, as observed in the case of two main sequence stars in close proximity. The dilemma arises: if neither star desires the mass, where does it dissipate? For stars that are more compact, this issue becomes more significant. Regardless of whether it's a main sequence star, a white dwarf, or a neutron star, the gravitational pull of a star depends solely on the distance from its center. gravity becomes stronger closer to the star's center. Consequently, the gravity at the surface of a white dwarf is much stronger than that of a normal star of the same mass, and even stronger at the surface of a neutron star. This means that if matter falls onto a normal star at a certain rate, it will release energy and produce luminosity at a particular rate upon impact with the stellar surface. However, if the same rate of mass transfer occurs onto a white dwarf, the energy released upon impact will be much greater, resulting in significantly higher heat and luminosity. The situation is even more extreme for a neutron star. Although a black hole doesn't have a surface, matter can still generate a significant amount of luminosity due to the strong gravity near the black hole. The luminosity produced by the falling matter can counteract its own descent. The outward flooding of luminosity exerts pressure. In some cases, such as with neutron stars, the luminosity can surpass the Eddington limit. This means that the luminosity generated by the falling matter is so intense that it prevents further descent. Even in less extreme scenarios, the energy from the fall can hinder it. Faced with this opposition, some of the matter won't accumulate on the star gaining mass, but will instead orbit both stars. In more extreme instances, the lost matter mainly orbits both stars, interacts, and expands into a roughly spherical gas cloud where the core of the mass-losing star and the mass-gaining star orbit. This configuration is termed a common envelope because the envelope of matter encircles both stars. This scenario significantly impacts the star's orbits. Instead of orbiting in the vacuum of space, they're now enclosed in a gas cloud. The gas hinders their movement, causing friction and drag, and their motion heats the gas. The drag slows down their forward velocity, causing the stars to spiral towards each other under the constant force of gravity. Consequently, they end up orbiting even faster, generating more friction, heat, and drag, which further accelerates the shrinking of their orbits. The energy and angular momentum lost from the stars are absorbed by the common envelope at an escalating pace. The specifics of this process remain unclear, but the principle of energy conservation sheds light on the overall sequence of events. As the gravitational energy from the contracting orbits diminishes, it eventually matches the gravitational energy binding the common envelope to the two stars. At this juncture, the energy imparted to the envelope by the star's motion is adequate to expel the envelope. This isn't an explosion, but rather a similar event to the ejection of a red giant's envelope to form a planetary nebula. The common envelope is ejected, and the two stars, the core of the mass-losing star and the mass-gaining star, irrespective of their configuration, resume orbiting in space. But now they're in very close proximity. Astronomers speculate that this process results in pairs of white dwarfs, neutron stars, and perhaps black holes, along with various combinations of these stars and normal stars. Now let's consider two stars that have evolved into compact forms: white dwarfs, neutron stars, or black holes after enduring mass transfer from the originally more massive star, then from the originally less massive star, and possibly through an intermediate common envelope phase. Now, they peacefully orbit in space. But is this the end of their journey? No. According to the general theory of relativity, gravitational waves propagate like ripples through curved space. Just as wiggling a rubber sheet or poking a finger into a still pond creates ripples, any disturbance in the curvature of space will generate waves that carry off energy and momentum. When two stars orbit each other, they cause rhythmic changes in the curvature of space around them, similar to twirling a paddle on a pond's surface. These changes create gravitational waves that spread through space, carrying energy and angular momentum away from the stellar orbits, causing the stars to gradually spiral closer together under the pull of gravity. Eventually, They are bound to collide in some manner. In certain rare but significant cases, this loss of energy can dictate the fate of stars. Stars, the cosmic titans that shape the very fabric of our universe, hold within them countless mysteries waiting to be unraveled. In this thrilling journey, we've barely scratched the surface. This is just the beginning of our quest for knowledge, the first chapter in our epic saga. But fear not, for the adventure has only just begun. Join me as we delve deeper into the enigmatic realms of space in the upcoming chapters of this exhilarating video series. Buckle up, stargazers, for we're about to embark on an odyssey to uncover the secrets of white dwarfs, pulsars, and more. Don't forget to hit that subscribe button to join me on this cosmic voyage. Until next time, may the stars guide you, and may your curiosity never dim.